We have been discussing Kirchhoff's laws. I will quickly again recall for you that Kirchhoff's laws consists of two laws. One is called the junction rule, where we said that at any junction which is defined by having at least three conductors joining at that point, I must have the algebraic sum of all the currents arriving there equal to 0. By algebraic sum, I mean I take, for instance, those which are arriving to be positive, those which are leaving to be negative, or vice versa. And a similar rule which says voltage rule, that is, if you go around any closed loop, then your net drop of the voltage is equal to 0. That is, you come back, return back to the same point. The point that I told you is that if you move in the direction of the current and pass through a resistance, then the potential will drop, that is decrease. And the other thing in the circuit, which is a battery, there when you travel from negative to the positive terminal, then the potential will increase. These are the two things that you have to remember, and based on that I have these Kirchhoff's laws. Last time we considered the problem of a cubical network of 12 equal resistances and obtained equivalent resistance between two diagonal coordinates. Now let us repeat the same problem, but with a slightly different pair of points about which, or I want the equivalent resistance between a different pair of points. Now you will see immediately how the symmetry changes. So let me look at it this way. Doesn't look like a cube, but so suppose I this time wanted that find the equivalent resistance between a point, let us say A, let me call this, give them the name A, B, C, D, E, F. So supposing this is what I wanted, between ends of a two diagonal on the base. Now look at this problem. The symmetry of the problem is not the same as before. So looking at this, I can see the following. I can immediately realize that all the four base points are identical, because with respect to A and E, these base points are symmetrically placed. So therefore, this path and that path are identical. So let us call the current to be I. But no longer that is true of this path, because this path which is here is not symmetric with respect to A and E's position. But however, something else is there. So what we said is that because of this symmetry, I must have the following, that the current in each one of these four paths will be identical. So I will write this way, that way, magnitudes will be the same. Now another point I can make is this, I don't know how much is the current here, we will work out. So let us just call it something at the moment. Now but another point I can make is this, that this top face, each one of the sides is also identical with respect to these 2 points. So therefore, these currents their magnitudes will also be the same. Supposing I double prime comes out, on this also there should be an I double prime, this must be another I double prime, this must be another I double prime. Now notice something interesting. What it tells me is this, that there are 2 paths in this where there are no currents. So this conductor and this conductor, no currents in this. In other words, even if you removed them, they will not participate in the circuit. And so you notice the major difference. Okay, so let us look at what is the situation here. This is all, I haven't still said what is this current as yet. So let us look at one of the things you immediately notice is this. By junction rule, this current which is coming into the point B must be equal to the sum of these two currents which are moving out. So therefore, this must be equal to 2I double prime. Earlier you remember in the previous case, I had I and I, but this is not true. Now if I now take a path A, B, so let me write down A, B, C, D, this path, here, 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 then E, F and A. Supposing I look at that path, this and that, that's a closed path, and apply the voltage rule there. So what am I getting? So notice this, I have a 2I there, times of course whatever is the resistance R. Let me take it as 1 so that I don't have to repeat that R all the time. Then plus I double prime, plus another I double prime. Now this one, because of the junction rule again must be 2I double prime. So plus 2I double prime minus this time, because I am traveling opposite, this is I. So minus I minus another I must be equal to 0. Actually, the entire thing, there is a common factor R that has been removed, because R is the resistance. So you notice immediately that what I am getting here is this 6I double prime equal to 2I. In other words, my I double prime is equal to I by 3. So if I double prime is I by 3, let us look at what is the current that is being supplied by the battery. Now notice my battery is supplying 2I plus 2I double prime. So 2I plus 2I double prime. So let's call that I in, that's 2I plus 2I double prime, and that's equal to 2I plus 2 by 3I, because I double prime is I by 3, which is equal to 8I by 3. So therefore, since V is the battery voltage, so I can write this as V equal to 8I by 3 times whatever is the equivalent resistance. Now notice, I can get an alternative expression by looking at, for example, what is the potential drop between A and E? That's what I am interested in. So I have an IR there and an IR there. So therefore, this is also equivalent to 2IR. So if you compare these two expressions, you find R equivalent equal to 3 by 4R. So let me look at now some problems where the symmetry is not obvious or there is a lack of symmetry. So let's look at another problem. there is no resistance there. Okay, let me take these numbers. 4 ohms, this is a 10 volt, let us suppose this is 1 ohm, this is 4 ohms, this is 2 ohms, this is 2 ohms, and this is a 5 volt battery. This circuit cannot be regarded as either a serial or a parallel combination of resistances. Now let us first use the junction rule to find out what are various currents. So I will do the following. Since this is the bigger box, bigger battery, as I have told you several times, you do not have to, but let me start by saying I1 this is supply. And let me say that on this branch I2 goes out. Now clearly at this branch I have I1 minus I2. So this I2 goes there, and let us say that this battery suppose is giving out a current I3. So that the current which is flowing through this is I2 plus I3. Everywhere I am using simply junction rule. So notice what has happened now. At this junction I2 plus I3 comes in and another I goes out, I1 goes out. So therefore at this junction it is I2 plus I3 minus I1, and that is going out. Algebraic sum is still 0. And clearly this current is also I3. I have got all the currents in there. Now since I have got 3 unknowns there, I1, I2 and I3, I require 3 loop equations. Remember, I have already exhausted my junction equations. So let me look at the first, the right hand side loop. So right loop. So you have to simply go like this. So minus, because I am going in the direction of current, I2 plus I3 into 2, that is the resistance, minus again I2 plus I3 minus I1 into 2, and I am climbing up the potential hill. So therefore plus 5 is equal to 0. Let us combine them. If you look at them, this becomes 2I1 minus 4I2 minus 4I3 is equal to 5. So that is your first equation. Let us look at this upper left loop. So I2 into 4, well minus because it is drop, minus I2 plus I3 into 2, then minus I1 into 1 because that is I1 plus 10 equal to 0. Simplifying them, you get I1 plus 6I2 plus 2I3 equal to 10. And finally the lower left, if you do lower left, this is again minus I1 minus I2 into 4. This time I am going against the direction of current. So therefore plus I2 plus I3 minus I1 into 2 minus I1 into 1, and that is equal to actually plus 10 equal to 0, so minus 10, and you simplify them you get 7I1 minus 6I2 minus 2I3 equal to 10. So these three equations provide you the necessary requirement for solving uniquely for the three variables I1, I2 and I3. I am not going to show you the algebra, but you can trivially show that I1 is 5 by 2 amperes, I2 is 5 by 8 amperes and I3 is 15 by 8 amperes. Let me consider another circuit where we can use symmetry to our advantage. So let's look at this circuit, and we are supposed to find out what is the equivalent potential across the point A and the point E. So look at this now. Let's assume that at the point A, I have a current I1 going on this branch and a current I2 going on this branch. Now by symmetry, I know that this and this side also must have I1 and I2. Only thing is we have to decide which one should be having I1 and which branch should be having I2. Now in order to do that, you notice the following, that this branch which is having I1 is in series with this branch BC. Now, so therefore, the current I1 flows through two resistances here. And if I am looking at the symmetry on this side, then it is this, at the point E, this resistance and these two resistances are connected. So therefore, this must be I1, because here two series resistances are there, and therefore this one must be I2. Now let's look at the junction rule at the point C. So here I have a current I3 which is equal to I1 minus I2. So basically you notice that by use of symmetry, I have reduced the number of unknowns to only two, I1 and I2. So let's look at what we can say about I1 and I2. First, let us look at this loop BC DAB. So if I do the loop rule here, I get minus I1R minus I1R. So this is minus 2 I1R, then minus again I1 minus I2 into R, and this time plus I2 into R, because I am traveling in the direction opposite to the current, and since there is no source in that branch, that's equal to 0. So if you simply simplify it, you will find I2 is equal to 3 by 2 I1. Now let us look at the other loop, namely, say remember I had only two unknowns there, so therefore I need the second loop with a V in it. So if you look at this loop here, that I have A, F, so let me design that, specify that loop, A, D, F, E, X, Y, A. So I've got minus I2 into R, then I have got I1R and another I1R, so minus 2 I1 into R plus V equal to 0, so that's equal to V. So therefore I have I2R plus 2 I1R equal to V, but I already know what is I2. So if you look at that, then I get I1 is equal to 2 by 7 V by R. So therefore I1 plus I2 is already calculated there. So that will work out to 5 by 7 V by R, because I2 is 3 by 2 and into 2 by 7, And suppose the equivalent resistance of this circuit is Req, then this is also equal to V divided by Req, because I1 plus I2 is the current that is supplied to the this circuit. So that tells me immediately that Req should be equal to 7 by 5R. As another example, let me look at this circuit, and once again I'll be using the symmetry of the problem to my advantage. So let us suppose this is I1 and this is I2. Now one thing I noticed is these two branches with respect to the point B is symmetrical as these two branches are with respect to the point A. So therefore, one of these branches must supply I1 and the other branch must supply I2. That is, one of these branches must take in I1 and another I2. The only thing that we have to decide is which one carries I1 and which one carries I2. So you notice one thing, that this is actually obvious, that resistance OB here is connected to the point B and to the point A through one resistance. So therefore, this is not identical to this resistance here, which is connected to the point A through these two resistances or any other two resistances. So that therefore, this one must be I1 and this one must be I2. So I can use the junction rule here now. Let me call this one as I3. So that this is I2 minus I3. And you can see here, since I1 is coming in, I1 is going out, so therefore this one must be I3, which was coming in from this branch. So let me now try to find out the relationship between them. Suppose I take this central loop. I already have used A, B, C, D. Let's call it EF. So let me take EFOE branch loop. So what do I have? I have an I3R minus I3R, another minus I3R, plus I2 minus I3 into R equal to 0. You simplify this, that gives you I3 equal to I2 by 3. Now let me look at, for instance, the left loop, which is EOAE. Now what do I have there? I have minus I2R minus I3R plus I1R equal to 0. So I already have a relationship between I2 and I3. I3 is I2 divided by 3. Put that back into this equation. You get a relationship between I1 and I2, and I2 turns out to be 3 by 4 I1. So therefore, the current supplied by the battery at the point A or flowing into the battery at the point B, which is equal to I1 plus I2. So I1 plus I2 is equal to 7 by 4 I1. But look at what statement I can make regarding how much is I1. So notice, if you look at this square loop, then what I have is I1R, or rather minus I1R minus I1R, which is minus 2 I1R plus V equal to 0. So which tells me that 2 I1R equal to V. so that I1 is equal to V by 12. So this, if you put it in I1 plus I2, you get 7 by 8 V by R, which must be identical to V by R equivalent. So that gives me R equivalent to be equal to 8 over 7 R. So in the last few lectures, including this one, we have talked about direct current circuits, including Kirchhoff's law, which is very useful in solving currents given voltages. I will end this series of lectures on direct current circuits or current electricity with couple of laboratory applications. The first one is known as a Wheatstones bridge. This is a circuit which is used to measure resistances. How do I measure resistance of an unknown sample in the laboratory? And in fact, this usually allows you to measure resistances in the range 1 ohm to 1 megohm with a 1% accuracy. It's a rather simple circuit, and the circuit works like this. You have a quadrilateral of resistance circuit. So let us assume these two R1 and R2 are given. So R1 and R2 are known resistances. Now R3 is a resistance which can be varied. There are sliders, variable resistances you can find. So R3 can be varied, known of course. And let me say Rx, this is the unknown resistance to be measured. Now the arrangement is like this. The circuit is made such that there is a ammeter or a galvanometer in the circuit, and across these points, which I will call as A and B, I connect a battery. So let us look at what happens. So there is a current which is coming in here. The current goes out like that and that. So let us call this I1, let us call this I2, as usual we have been doing. Then this current would normally go through this and that, it will divide here, and the circuit will be complete. Now what we do is this, we adjust the resistance R3. So let me, because it is an important point, let me talk about adjust R3, the variable resistance. Till such time that there is no current passing through the ammeter. This is generally known as a null deflection, that is, galvanometer or the ammeter does not show any deflection. So that is null deflection. Now you see what happens is this. When there is null deflection, this current I1 which is coming from here, sorry, this is this I equal to I1 plus I2. That will all pass through this one. And likewise, this I2 which is coming in here will go through this. So if you now look at this circuit, so you notice I1 R1 0 minus I2 R2. So I1 R1 equal to I2 R2. I3 R3 minus I2 Rx. So therefore, I1 R3 is equal to I2 Rx when null deflection takes place, so that this section does not contribute. So if you look at the resistances there, then you will immediately find out by dividing one equation with the other that R1 by R3 equal to R2 by Rx. Now, so therefore, when values of R1, R2 are known and R3 we determine experimentally by varying the resistances till I get a null deflection, I can calculate Rx by the formula that Rx is equal to R2 by R1 into R3. So this is the principle of Wheatstone's bridge, in which you have a bridge in which through which this connecting the bridge, it does not give you any deflection. Suppose I have R1 equal to 6 ohms, R2 equal to 1.5 ohms, and let us suppose my null deflection has been achieved by having R3 equal to 8 ohms. Then of course Rx will turn out to be R2 by R1 into R3, which is equal to 2 ohms. It is trivial. But suppose my Rx is slightly different. Supposing Rx is, let us say, 2.01. You can use the same circuit, but you will now find that there will be a current in the passing through the emitter. It will be small because my deviation here is small. Now, an interesting application of this is the following. Let me look at a slightly different circuit. Let me give some name. Suppose each one of them is R. The problem is, find the equivalent resistance between A and B. Once again, the circuit is neither a series combination nor a parallel combination, and it is very difficult to do it by that method. So remember again what we said. We said that in which case you should imagine between A and B you have a battery. I could do that. But let me make each one of them the same, and let us suppose this I call it as an R prime. Now something interesting actually happens, that if you look at it carefully, you will find that this circuit is nothing but a Wheatstone's bridge. And in order to do that, you have to recollect back how the connections are made. So let me give it some numbers. Let's call this C, let's call this D. So this point is B, this point is A, because this is the same point. So look at what are the various connections. My point A is connected to C through a resistance R and to D through a resistance R. The point B is connected to C through a resistance R. Again, it is connected to D through a resistance R. And CD are connected by a resistance R prime. Now compare this with the circuit that I had. This was my A. So this is C, this is D. So notice A is connected to C and to D. B is connected to C and to D. And CD is connected through the ammeter and through any resistance that may be there. So with these ideas, let me redraw that circuit again. So look at what will happen if I drew the circuit again. This is the way our connections are in that circuit. Now, but if you look at it, since this by this is this by that, this is a balanced Wheatstone's bridge. Which implies that no current is flowing through the branch CD. No current through CD. So therefore, what I can now do is this, since there is no current in CD and I am required to find out the effective resistance between the points A and B, I can now redraw that circuit as follows, that I have these points A and B, and if this is basically absent, what I have is a series resistance R plus R, namely 2R between A and B, and another pair which also works out to 2R from the lower branch. So this is 2R, this is 2R, which tells me that the equivalent resistance is simply R. So this problem is interesting because on the first look it doesn't look like a Wheatstone's bridge, but on the other hand, once you have realized what is connected to what, it can be shown to be equivalent to a Wheatstone's bridge. One of the applications of Wheatstone's bridge is what is known as a meter bridge. So this is the diagram of a meter bridge. So basically, the reason why it's called a meter is the following, that this has a wire of length 1 meter, uniform cross section, which is stretched and is fixed to the points A and B. Now, these connectors, they are low resistance connectors. There are two gaps in these low resistance connectors. Across one, there is a wire of resistance R, and across the other, there is a known resistance S, and the two ends A and B are also connected to a battery with a key. Now, so this is basically a Wheatstone's bridge, and what one does is that one point of the one end of the galvanometer is connected to the middle point here, and the other one can slide on AB, and one slides it till you receive or till you get a null deflection. So no current through galvanometer. Now notice one thing, if rho is the resistivity of the material of the wire AB, and suppose I have achieved a null deflection when this length is L, let's take L centimeters, so that this one is 100 minus L centimeters. So according to the principle of Wheatstone's bridge that we did, when there is null deflection, I get R by S must be balanced by resistance of the section AD divided by the resistance of the section DB. Since resistance of the section AD is the resistance of the wire of length L centimeter, we write this as rho L1 by or rho L by A, where the unit of rho is in ohm centimeter and L1 is in centimeter or L is in centimeter, and this divided by rho times 100 minus L divided by A, which is nothing but L by 100 minus L. So by finding out at what length the null deflection is achieved, using a meter bridge, an unknown resistance R can be determined. Yet another application of the principle of Wheatstone's bridge is in what is known as a potentiometer, which I have shown here in the diagram. So potentiometer has basically two utilizations in the laboratories, and the first one is to compare EMF of two or more cells. Now the arrangement is something like this. So there is this main circuit with a source of voltage V, and there is a variable resistance here which is varied so that the deflection of the galvanometer at the two ends comes within the range of the galvanometer. There is a switch which can be closed and thereby enabling the source V here to send a constant current through the circuit. Now what happens is this, that this part AB, these are all resistanceless wires. So between the point AB is a long uniform wire which usually has several turns as is shown here, but for convenience I have simply put it stretched between the points A and B of the circuit. Now the point A is connected to the two sources of EMFs which we want to compare. The EMF source number 1 is connected to a three-way switch to, let us say, point number 1, and similarly the source 2 is connected to the second point of the three-way key, and there is a common point 3 which is connected to a galvanometer and to a wire which can slide over AB. The basic principle is the following, that let us say we connect 1 to 3, meaning thereby that the EMF source E1 is in the circuit but E2 is not. This switch S is kept closed. Now what we do is this, we slide this wire which is connected to the other end of the galvanometer such that a null deflection is obtained. So when the null deflection is obtained, we immediately see that in this situation, A, P, E1, R1, which is the internal resistance, the point 1, the point 3, G, which is the galvanometer, and let us say the null deflection is obtained at the point N1, this section has no current because there is no deflection in the galvanometer. However, because the V sends a constant current through the section BA, there is a potential drop across the wire AB. So there is a potential drop in the wire AB. And since the null deflection is obtained at the point N1, it tells me that the potential drop in the section A N1 is balanced against the EMF that is supplied by the battery. Now note one thing, that because there is no current in this part of the circuit, the internal resistance does not play a role, because internal resistance would have provided a further potential drop if there were a current in this part of the circuit. So therefore, the potential drop across A N1 is the potential drop across P E11. Now, suppose the length for which we obtain the null deflection is given by L1. Then what we find is this, I times the resistance of the section A N1 is equal to E1, but how much is this? This is equal to rho the length L1 divided by A, and that's equal to E1. Now that tells me that I could repeat the same thing for when the EMF source E2 is connected, namely instead of 1, 3 being connected, if I connected 2, 3. Now in that case, suppose the null deflection is obtained at a point L2, which is a length L2 there, then what I have is a very similar expression, which I will write here, that I times R A N2, which is equal to rho L2 by A, and that must be equal to E2. The reason is again the same, that because there is no current in that section of the circuit, the internal resistance does not play any role. So therefore, the ratio of E1 to E2 is simply equal to L1 by L2, and this is just the ratio of the lengths of the wire for which the null deflection is obtained. Yet another application of the potentiometer in the laboratory is to determine the internal resistance of a battery. The circuit is more or less similar to what we showed in the previous case, and what we have here is this, that as before I have a main circuit consisting of the potentiometer wire, which, as I have said earlier, actually consists of several loops of wire, but I have just shown it as stretched between the points A and B. V is a external source which supplies me a constant current through the wire AB, and this is a key K1 which will remain closed. There is a variable resistance RV as before, which is adjusted so that the galvanometer reading comes between the section A and B. Now there is a modification in this part of the circuit. This is the EMF whose internal resistance we are interested in determining. So what happens is this: in this part of the circuit there is another resistance, usually a resistance box, and a key K2 which is adjusted, which can be either closed or open. So in the first part of the operation we have the key K1 closed. Of course K1 will remain closed for even the second section, and K2 is kept open. Now when K2 is open, this part of the circuit, C, D, R, K2, etc., that part of the circuit doesn't participate. Repeat, when K2 is open, there is no current in this part of the circuit, and if we adjust the sliding wire's position so that null deflection is obtained, let's say it is obtained at a distance L1 from A. So this distance is L1. Now because there is no current in this part of the circuit, the potential drop because of the EMF is balanced by the potential drop for the section A times N1. So suppose in this situation null deflection is obtained at N1, then what happens is this potential drop across AN1 balances the EMF E. Now as I have said in the other part also, that since there is no current through this section CD, let us say, the internal resistance does not play any role in this process. Now let's look at how much is the drop. Now notice that this battery is providing a constant current I. So current through the wire AB is given by I equal to V divided by RV, that is the variable resistance, plus R prime, where R prime is the resistance of the entire length AB of the wire of length, let us say L. Because the wire is of uniform cross section, there is a constant potential gradient along the wire, and that is easily calculated by finding out, since I know the current, so the resistance is R prime for the entire wire, the potential gradient, which I will represent by phi, is this current I, which is V by RV plus R prime multiplied by R prime, of course. This is essentially the potential drop per unit length. Now since the balance has been obtained at a length L1 and it has been balanced against the EMF E, I have, for the first part of the operation, when the null deflection is obtained, E is equal to phi L1. Let us emphasize by saying for null deflection. Now in the second part of the circuit, what I will have is, I will also close K2. Now let's see what happens when K2 is closed. Now when K2 is closed, this source of EMF E sends a current through this part of the circuit. Now at that stage what happens is this, that I again adjust the length so that the null deflection is obtained at a point N2. Let's say that that length is L2. But this time when I receive a null deflection, because there is a current through this part of the circuit, it means that that current, which we will just now write down how much, will also give a drop across the internal resistance R. And let's see how it works. So with K2 closed, the cell with EMF E sends a current. And how much is that current? Let's call it I prime, and that is obviously equal to E divided by R plus R prime, R plus small r, where this R is the resistance which is in this part of the circuit. So as a result, what happens is the potential drop across that CD, which was earlier E when K2 was open, now is reduced by an amount I prime times that smaller. So therefore the potential drop across CD is E minus I prime R, and that must be equal to the gradient phi multiplied by L2, the distance at which I obtained a null reflection. And since this is equal to E R divided by R plus R, so that is equal to phi L2. The reason is that I have this amount, E minus I prime R, is the potential drop across these 2 points. So therefore whatever is the current multiplied by this resistance R gives me the potential drop across these 2, or that is the potential drop across CD. So that's my phi L2. But we had seen that E was equal to phi L1. Now you simply substitute for E there and equate it to phi L2, and that enables you to determine R in terms of L1, L2 and the resistance R. With this we come to the end of our series of lectures on direct current circuits.